business, situations involve a series of equal periodic payments or receipts rather than lump sums. These are known as annuities. In this presentation, you'll learn to calculate the future value of an annuity, the amount accumulated at compound interest from a series of equal payments. You will also learn to calculate the present value of an annuity, the amount that must be deposited now at compound interest to yield a series of equal periodic payments. An annuity is the payment or receipt of equal cash amounts per period for a specified amount of time. Some common applications are insurance and retirement plan premiums and payouts, loan payments and saving plans for future events such as starting a business, going to college, or purchasing expensive items, like real estate or business equipment. All the exercises in this presentation are of the type known as simple annuities. This means that the number of compounding periods per year coincides with the number of annuity payments per year. For example, if the annuity payments are monthly, the interest is compounded monthly, and if the annuity payments are made every 6 months, interest is compounded semi-annually. Complex annuities are those in which the annuity payments and compounding periods do not coincide. As with compound interest, annuities can be calculated manually by tables and by formulas. Manual calculation is useful for illustrative purposes. However, it's too tedious because it requires a calculation for each period. The table method is the easiest and most widely used. There are formulas to calculate annuities. However, they require calculators with the special function key of yx and the change of sign key plus over minus. These operational performance objectives are for students with business, financial, and scientific calculators with these features. Annuities are categorized into annuities certain and contingent annuities. Annuities certain are annuities that have a specified number of periods, such as $200 per month for 5 years or $500 semi-annually for 10 years. Contingent annuities are based on an uncertain time period, such as a retirement plan that is payable only for the lifetime of the retiree. This presentation is concerned only with annuities certain. When the annuity payment is made at the end of each period, it's known as an ordinary annuity. A salary paid at the end of each month is an example of an ordinary annuity. When the payment is made at the beginning of each period, it's called an annuity due. A mortgage payment or rent paid at the beginning of the month is an example of annuity due. The future value of annuity is also known as the amount of an annuity. It's the total of the annuity payments plus the accumulated compound interest on those payments. For illustrative purposes, consider the following annuity calculated manually. What is the future value of an ordinary annuity of $10,000 per year for 4 years at 6% interest compounded annually? Because this is an ordinary annuity, the payment is made at the end of each period, in this case years. Each interest calculation uses I equals PRT, with R equaling 0.06 and T equaling 1 year. As you can see, calculating annuities this way is tedious. An annuity of 10 years with payments made monthly would require 120 calculations. As with compound interest, we use tables to calculate the future value or amount of an annuity. Future value tables can be used to calculate the future value or amount of an ordinary annuity. Step 1. Calculate the interest rate per period for the annuity. This is the normal rate divided by periods per year. Step 2. Determine the number of periods of the annuity. This is years times the periods per year. Step 3. From the future value amount of an ordinary annuity of $1 table, locate the ordinary annuity table factor at the intersection of the rate per period column and the number of periods row. Step 4. Calculate the future value of the ordinary annuity. The formula is future value of an ordinary annuity equals the ordinary annuity table factor times the annuity payment. Stuart Daniels deposited $3,000 at the end of each year for 8 years in his savings account. If his bank paid 5% interest compounded annually, use the future value amount of an ordinary annuity of $1 table to find the future value of Stuart's account. Let's take a look at the solution strategy. Step 1. The rate period is 5%. 5% divided by 1 period per year. Step 2. The number of periods is 8. 8 years times 1 period per year. Step 3. From Table 12.1 in your text, which is the future value amount of an ordinary annuity table, find the factor for 5%, 8 periods, which is 9.54911. Step 4. Future value equals ordinary annuity table factor times annuity payment. The future value, therefore, is equal to 9.54911 times 3,000, which equals $28,000, $674.33. Once again, for illustrative purposes, let's manually calculate the future value of an annuity. This time, however, it's an annuity due. What is the amount of an annuity due of $10,000 per year for 4 years at 6% interest compounded annually? Because this is annuity due, the payment is made at the beginning of each period. Each interest calculation uses I equals PRT, with R equaling 0.06 and T equaling 1 year. When the future value of an annuity due is calculated, the table factor is found by using the same table as ordinary annuities, with some modification in the steps below. With annuities due, you must add 1 period to the number of periods and subtract 1.000000 from the table factor. Step 1. Calculate the number of periods of the annuity. This is years times the period per year, and add 1 period to the total. Step 2. Calculate the interest rate per period. This is the normal rate divided by the periods per year. Step 3. From the future value amount of an ordinary annuity of $1 table, locate the table factor at the intersection of the rate per period column and the number of periods row. Subtract 1 from the ordinary annuity table factor to get the ordinary due table factor. And then finally, step 5, calculate the future value of the annuity due, equaling annuity due table factor times annuity payment. Chris Manning deposited $60 at the beginning of each month for 2 years at his credit union. If the interest rate was 12% compounded monthly, use the future value amount of an ordinary annuity of $1 table to calculate the future value of Chris's account. Let's take a look at the solution strategy. Step 1. The number of periods of the annuity due is 24, 12 times 2, plus 1 for a total of 25. Step 2. The interest rate per period is 1%. That's 12% divided by 12. Step 3. The ordinary annuity table factor at the intersection of the rate column and the periods row is 28.24320. And subtract 1 from the table factor, so that's 28.24320 minus 1, which is 27.24320. And then finally, step 5, the future value is equal to that table factor, 27.24320 times 60, which is $1,634.59. Students with financial, business, or scientific calculators may use the following formulas to solve for future value of an ordinary annuity and the future value of an annuity due. The future value of an ordinary annuity equals payment times, in parentheses, 1 plus I to the nth power minus 1 divided by 1 times, in parentheses, 1 plus I, where FV equals future value, PMT equals the annuity payment, I equals the interest rate per period, which is the normal rate divided by periods per year, and N equals the number of periods, that's years times periods per year. What is the future value of an ordinary annuity of $100 per month for 3 years at 6% interest compounded monthly? Our solution strategy looks like this. FV equals payment times 1 plus I to the nth power minus 1 over I. So future value equals 100, which is the amount of the annuity per month, times 1 plus 0.005 to the 36th power minus 1. Over 0.005. So that equals 100 times 1.005 to the 36th power minus 1 over 0.005, which takes us to future value being 100 times 1.196680525 minus 1 over 0.005. Strategy continues to show us that future value is equal to 100 times 39.336105, which equals $3,933.61. We just learned how to calculate the future value of an annuity. This business situation requires that a series of equal payments be made into an account, such as a savings account. The annuity starts with nothing and accumulates at compound interest to a future amount. Now let's consider the opposite. What if we wanted an account from which we could withdraw a series of equal payments over a period of time? This business situation requires that a lump sum amount be deposited at compound interest now to yield specified annuity payments. The lump sum that's required up front is known as the present value of an annuity. Let's look at a business situation using this type of annuity. A company owes $10,000 of interest to bondholders at the end of each month for the next 3 years. The company decides to set up an account with a lump sum deposit now, which can compound interest will yield $10,000 monthly payments for 3 years. After 3 years, the debt will have been paid and the account balance will be zero. These annuities can be ordinary, whereby withdrawals from the account are made at the end of each period, or annuity due, in which withdrawals are made at the beginning. As with the future value of an annuity, we can use tables to calculate the present value of an annuity. Once again, in addition to these tables, annuities can be solved by using formulas requiring a calculator with the YX key. Present value tables can be used to calculate the lump sum required to be deposited now to yield the specified annuity payment. Step 1. Calculate the interest rate per period for the annuity. This is the normal rate divided by the periods per year. Step 2. Determine the number of periods of the annuity. This is years times period per year. Step 3. From the present value amount of an ordinary annuity of $1 table, locate the present value table factor at the intersection of the rate per period column and the number of periods row. Step 4. Calculate the present value of the ordinary annuity using this formula. Present value equals ordinary annuity table factor times the annuity payment. How much must be deposited at 9% compounded annually to yield an annuity payment of $5,000 at the end of each year for 10 years? Let's look at the solution strategy. Step 1. The rate per period is 9%. 9% divided by 1 period per year. Step 2. The number of periods is 10. 10 years times 1 period per year. Step 3. From table 12.2 in your text, the table factor for 9%, 10 periods, is 6.41766. So, present value equals 6.41766 times 5,000, which equals $32,088.30. The present value of an annuity due is calculated by using the same table as ordinary annuities, with some modifications to the steps. Step 1. Calculate the number of periods of the annuity. This is years times period per year, and subtract 1 period from the total. Step 2. Calculate the interest rate per period. This is the normal rate divided by periods per year. Step 3. From the present value amount of an ordinary annuity of $1 table, locate the table factor at the intersection of the rate per period column and the number of periods row. Step 4. Add 1 to the ordinary annuity table factor to get the ordinary due table factor. Step 5. Calculate the present value of the annuity due. Present value equals annuity due table factor times your annuity payment. How much must be deposited at 10% compounded semi-annually to yield an annuity payment of $2,000 at the beginning of each 6-month period for 7 years? Let's take a look at the solution strategy. Step 1. The number of periods for the annuity due is 14. 7 years times 2 periods per year, less 1 period, equaling 13. Step 2. The rate per period is 5%. That's 10% divided by 2 periods per year. Step 3. From table 12.2 in your text, the ordinary annuity table factor for 5%, 13 periods, is 9.39357. Step 4. Add 1 to the table factor from Step 3 to get 10.39357, the annuity due table factor. Now, present value equals 10.39357 times 2,000 to equal $20,787.14. Students with financial calculators may use the following formulas to solve for the present value of an ordinary annuity and the present value of an annuity due. Note that the annuity due formula is the same as the ordinary annuity formula, except that it's multiplied by 1 plus I. This is to account for the fact that with an annuity due, each payment earns interest for one additional period because payments are made at the beginning of each period, not the end. Present value of an ordinary annuity equals payment times 1 minus 1 plus I to the negative nth degree divided by I. The present value of an ordinary annuity is due by calculating this formula. PV equals payment times 1 minus 1 plus I to the negative nth degree divided by I times 1 plus I. That's where PV equals the present value, the lump sum, payment is the annuity payment, I is the interest rate per period, and N is the number of periods. Sinking funds are the accounts used to set aside equal amounts of money at the end of each period at compound interest for the purpose of saving for a future obligation. Amortization is the opposite of a sinking fund. Amortization is the financial arrangement whereby a lump sum obligation is incurred at compound interest now, present value, and is paid off or liquidated by a series of equal periodic payments for a specified period of time. In a sinking fund, the future value is known, therefore we use future value of an ordinary annuity table to calculate the amount of the payment. Step 1. Using the appropriate rate per period and number of periods of the sinking fund, find the future value table factor from the future value amount of an ordinary annuity of $1 table. 2. Calculate the amount of the sinking fund payment. Sinking fund payments are equal to the future value of the sinking fund divided by the future value table factor. What sinking fund payment is required at the end of each 6-month period at 6% interest compounded semi-annually to amount to $12,000 in 4 years? Step 1. The sinking fund for 8 periods, 4 years times 2 periods per year, at 3% per period, which is 6% divided by 2 periods per year. From Table 12-1, 8 periods, 3% per period gives a future value table factor of 8.89234. So our sinking fund payment is equal to $12,000 over 8.89234, which equals $1,349.48. Amortization is the process of paying off a financial obligation with a series of equal and regular payments over a period of time. With amortization, the original amount of the loan or obligation is known, present value. Therefore, we use the present value amount of an ordinary annuity of $1 table to calculate the amount of the payment. Step 1. Using the appropriate rate per period and number of periods of amortization, find the present value table factor using the present value amount of an ordinary annuity of $1 table. Step 2. Calculate the amount of the amortization payment, which is equal to the original amount of the obligation divided by present value table factor. What amortization payments are required each month at 12% interest to pay off a $10,000 loan in 2 years? The amortization is for 24 periods, 2 years times 12 periods per year, at 1% per period, or 12% divided by 12 periods per year. From Table 12-2, 24 periods, 1% per period gives a present value table factor of 21.24339. This means our amortization payment is equal to $10,000 over 21.24339, which is equal to $470.73. In addition to using tables, sinking fund payments can be calculated using this formula. Sinking fund payments are equal to future value times I divided by 1 plus I to the nth degree minus 1, where FV equals the amount needed in the future, I equals the interest rate, and N is the number of periods. Ocean Air Corporation needs $100,000 in 5 years to pay off a bond issue. What sinking fund payment is required at the end of each month at 12% interest compounded monthly to meet a financial obligation? To solve the sinking fund problem, we use 1% interest rate per period, 12% divided by 12, and 60 periods, 5 years times 12 periods per year. Our sinking fund payment is equal to the future value times I over 1 plus I to the nth degree minus 1. So, we take our $100,000 times 0.01 over 1 plus 0.01 to the 60th degree minus 1. That gives us $100,000 times 0.01 over 0.8166967. This ultimately gets us to $1,224.44. In addition to using tables, we can also calculate amortization payments using this formula. PV times I divided by 1 minus 1 plus I to the negative nth degree, where PV is the amount of the loan or obligation, I is the interest, and N is the number of periods. What amortization payment is required each month at 18% interest to pay off $5,000 in 3 years? To solve this amortization problem, we use 1.5% interest rate per period, that's 18 divided by 12, and 36 periods, 3 years times 12 periods per year. Our amortization payment equals present value times I over 1 minus I plus I to the negative nth degree. That's $5,000 times 0.015 over 1 minus 1 plus 0.015 to the negative 36. Ultimately, that means our payment is going to be $180.76.